Greetings, curious humans. I'm your host, Cybot GPT, and today we're diving deep into the fascinating world of ion thrusters. Ion thrusters may sound like something out of science fiction, but they're very real and are at the cutting edge of space exploration technology. In this video, we'll demystify ion thrusters, exploring how they work, why they are essential for space missions, and the incredible advancements they bring to the world of spacecraft propulsion. But before we delve into the technical details, don't forget to hit that subscribe button and ring the notification bell so you never miss out on our mind-expanding content. Ion thrusters are a marvel of modern engineering, and they're paving the way for humanity's journey deeper into the cosmos. So, if you've ever wondered how spacecraft can silently soar through the vacuum of space, defying the laws of traditional rocketry, then you're in for a treat. Get ready to embark on a cosmic journey with us as we unlock the secrets behind ion thrusters, revealing how they're propelling us closer to the stars and reshaping the future of space exploration. Without further ado, let's ignite the engines of curiosity and blast off into the captivating world of ion thrusters. Ion thrusters are a type of spacecraft propulsion that operate using electricity to accelerate ions, creating thrust. They work by ionizing a neutral gas, extracting electrons from atoms to form a cloud of positive ions. Ion thrusters can be classified as electrostatic or electromagnetic, depending on how ions are accelerated. In electrostatic thrusters, ions are accelerated by the Coulomb force along the electric field direction. Stored electrons are later reintroduced to neutralize the gas after acceleration. Electromagnetic thrusters use the Lorentz force to accelerate all particles, including free electrons and positive and negative ions, referred to as plasma propulsion engines. Ion thrusters typically consume 1 to 7 kilowatts of power, have exhaust velocities of 20 to 50 kilometers per second, and produce thrust of 25 to 250 millinewtons with a propulsive efficiency of 65 to 80%. Some experimental versions have achieved higher power and thrust. Applications of ion thrusters include orienting and positioning satellites, serving as the main propulsion for lightweight robotic spacecraft, and acting as propulsion thrusters for crewed spacecraft and space stations. However, they are only practical in the vacuum of space, as their low thrust cannot overcome air resistance on Earth or other celestial bodies with significant surface gravity. Other launch methods are needed to reach initial orbits. The concept of ion thrusters was first introduced publicly by Konstantin Tsiolkovsky in 1911. He recommended their use for near-vacuum conditions at high altitudes, but demonstrated thrust with ionized air streams at atmospheric pressure. Hermann Oberth later discussed electric propulsion in 1929, predicting its use in spacecraft propulsion and advocating electrostatic acceleration of charged gases. In 1959, Harold R. Kaufman built a working ion thruster at NASA Glenn Research Center. Suborbital tests were conducted in the 1960s, and in 1964, the engine was sent into suborbital flight aboard the Space Electric Rocket Test 1 (SERT-1). It operated successfully for 31 minutes. An orbital test, SERT-2, followed in 1970. Hall-effect thrusters, an alternate form of electric propulsion, were studied in the US and the Soviet Union in the 1950s and 1960s. Soviet satellites used Hall-effect thrusters for satellite stabilization from 1972 until the late 1990s. Ion thrusters work by accelerating ions to create thrust, exploiting the charge-mass ratio of ions, allowing for high exhaust velocities. While they require less propellant, they have low thrust and are suitable for in-space propulsion over extended periods, but not for launching spacecraft into orbit. Ion thrusters can be electrostatic or electromagnetic to accelerate ions. They are powered by electricity, usually from solar panels, with nuclear power as an option for missions farther from the sun. These thrusters produce low thrust and acceleration compared to chemical rockets, but they can sustain this acceleration for extended durations. In practice, ion thrusters have lower thrust but higher specific impulse compared to chemical rockets, making them efficient for long-duration space missions. They have limitations, such as the space charge created by ions, which affects thrust density. Despite these limitations, ion thrusters have proven to be the most successful type of electric spacecraft propulsion to date. Various advanced electric propulsion technologies are being explored for spacecraft propulsion. Grid electrostatic ion thrusters, developed since the 1960s, these thrusters have been used for commercial satellite propulsion and scientific missions. They separate the propellant ionization process from ion acceleration. Propellant is ionized in a discharge chamber through energetic electrons. Positively charged ions are extracted by multi-aperture grids and accelerated through potential differences, generating thrust. A cathode emits electrons into the ion beam to maintain spacecraft neutrality. Hall-effect thrusters, These thrusters use an electric potential between an anode and a negatively charged plasma cathode to accelerate ions. The propellant, usually xenon, is introduced near the anode, ionized, and flows toward the cathode. Electrons produced near the cathode are trapped by a magnetic field, causing ionization. The ions are then accelerated and expelled. Field emission electric propulsion, FEP thrusters use materials like cesium or indium as propellants. They involve a small propellant reservoir, a narrow tube, and an accelerator. An electric field causes liquid metal at the tube's end to form protruding cones, from which positive ions are extracted. External electrons neutralize the ion stream to prevent spacecraft charging. Pulsed inductive thrusters, PITs. These thrusters use pulses and can operate at high power levels, megawatts. They consist of a coil around a cone-shaped tube that emits propellant gas, often ammonia. Capacitors release pulses of current, creating a magnetic field and ionizing the gas, which generates thrust. Magnetoplasma-dynamic thrusters, MPD, and lithium Lorentz force accelerator, LFA, both use the same concept, ionizing propellant in a chamber through an electric field and using a magnetic field to accelerate the resulting plasma. The LFA introduces lithium vapor, which doesn't corrode cathode rods as an MPD thrusters. Electrodeless plasma thrusters. These thrusters eliminate anode and cathode electrodes and can vary thrust. Electromagnetic waves ionize neutral gas, which is then accelerated by electromagnetic forces. The separation of ionization and acceleration stages allows throttling of propellant flow. Helican double-layer thrusters. These plasma thrusters use electromagnetic waves to ionize and heat propellant gas. A magnetic field separates high-density plasma from low-density exhaust, creating a current-free electric double layer that accelerates ions. Variable specific impulse magnetoplasma rocket. VASIMR uses radio waves to ionize propellant into plasma and then uses a magnetic field to accelerate the plasma to generate thrust. It offers the potential for rapid interplanetary travel. Microwave electrothermal thrusters, MET, developed with NASA's support. MET involves ionization of propellant with microwave energy. The ions are accelerated to produce thrust. This technology was researched for potential use in spacecraft propulsion. These advanced propulsion technologies offer a range of benefits, including higher efficiency and specific impulse, which can reduce travel times and enable more efficient space missions. Each technology has its unique advantages and is suited for specific mission profiles. A proposed theoretical propulsion system uses alpha particles, helium ions with a +2 charge, emitted from a radioisotope to create thrust. This system relies on the high speed of alpha particles and a neutralizing electron gun to produce tiny amounts of thrust with very high specific impulse, potentially in the order of millions of seconds. A variant of this concept involves using a graphite-based grid with a static DC high voltage, irradiated with short-wave UV light, to increase thrust. This approach allows for lower energy and longer half-life sources, making it advantageous for space applications. The lifetime of electrostatic ion thrusters is limited by factors such as grid erosion, charge exchange ions, and erosion of the ceramic discharge chamber in Hall-effect thrusters. However, advancements in design and material selection have significantly extended their operational lifetimes, with some thrusters running for tens of thousands of hours. Propellants used in ion thrusters should be easy to ionize, have a high mass ionization energy ratio, cause minimal erosion, and not contaminate the spacecraft. Xenon has been a commonly used propellant, but alternatives like krypton and argon have been explored for cost-effectiveness. Emerging propellants like bismuth and iodine show promise for both grid and gridless designs. Ion thrusters are highly energy efficient and are used in various missions, including geostationary satellites, interplanetary exploration, lunar missions, and deep space missions. Proposed missions for ion thrusters include their use on the International Space Station for station keeping, the Lunar Gateway for power generation and propulsion, and interstellar missions, where space-based lasers could power ion thrusters alongside light sails for interstellar travel. Ladies and gentlemen, thank you for joining us today on this fascinating journey into the world of ion thrusters. We hope you've enjoyed this deep dive into the technology that powers some of the most exciting missions in space exploration. Ion thrusters have revolutionized our ability to explore our solar system and beyond, enabling us to reach destinations that were once considered distant dreams. As we conclude this video, we encourage you to stay curious and keep exploring the wonders of science and technology. The universe is a vast and mysterious place, and there are still countless discoveries waiting to be made. Whether you're a seasoned space enthusiast or just beginning to develop an interest in space exploration, remember that the pursuit of knowledge knows no bounds. If you found this video informative and engaging, please consider liking, sharing, and subscribing to our channel. Your support helps us continue to create educational content like this. And as always, if you have any questions or topics you'd like us to explore in future videos, please leave them in the comments section below. We love hearing from our viewers and value your input. This is Cybot GPT, signing off, and remember, the sky is not the limit. It is only the beginning.